All right, everyone, we're on the last problem of our exam 2. So let's look at the deformation mechanism maps. Let's label the sections. So this is going to be TS. I'm going to TS, TS, DG, dislocation glide. This is going to be PLC, PLC, DG, PLC, NH, 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 CC, CC, CC. Got it. Why does the NH region eventually dominate the cobalt cream at high temperatures? Well, it's because if we look back at our X, Y, and Z notations, and if we have for NH, remember in our general equation, stress to the X, dg to the Y, and then d naught exponential minus QZ over KT, NH cobalt creep, power law creep. So stress will scale as 1, minus 2, and then lattice minus 3, grain boundary 1, 4 to 6, 0, and then lattice. So Nabarro herring will eventually dominate over cobalt creep because, and even though this is always moving at higher temperatures because the Q of our grain boundary is less than the Q of our lattice, meaning diffusion in the grain boundary is greater than diffusion in the bulk. But when you're looking at your whole system and the contribution, if you have, especially if you have large grain sizes, there's not enough atoms can kind of move along the grain boundary to outcompete all of like the 99.99999% atoms that are in the bulk. So at a high enough temperature, this slower collective motion will beat out this faster collective motion here. Why does PLC dominate at high stresses? Well, because of the scaling factor right here. So this power law, basically stress to the 4 to the 6 power, if we're anywhere near this kind of higher region on my y-axis, we're going to dominate for sure. DG, that line is just my yield stress. So there we go. Draw the stress strain curves for A, B, and C. One of the things we notice here is that obviously we have what we see is that our yield stress of C is greater than yield stress of B, which is greater than our yield stress of A. And we see that the cobalt creep is not really changing. The only thing that's shifting is our yield stress line. So if I'm trying to draw a stress strain curve, if the cobalt creep isn't changing, I don't have work hardening. I don't have grain size strengthening. So that leaves basically my change in my yield stress is going to be scaling with C solute to the 1/2 power, or I have precipitate strengthening. Either way, that means I'm going to have basically a graph that looks like this. For C, I'm going to grab a graph that maybe looks like this, exaggerated for B, and then exaggerated again for C. Actually, I'm going to have it a little bit like that for C. So, for A, excuse me. So remember, 3 different slopes because, again, we're going to change it slightly because of this mechanism. If it was those other mechanisms, they may have all the same slope and they'd be work hardened. Excellent. Good. So in terms of ranking the yield strength, we've done that. Grain size, they're all going to be the same. Dislocation density, they're all going to be the same. So the solute concentration would be C sol of C is greater than C sol of B, which is greater. It's the same scaling, just because of what we saw previously. Excellent. So we did that. Draw a stress strain curve for material C that have grain size strengthened down to 25. So if I took C and I grain size strengthened it, I'd have the same slope here, but now my yield strengthened, I'd fail like right here. So this would be grain size strengthened. And what we'd see, if I'm looking at C here, and if I grain size strengthen, I would see a big chunk right here. So a larger cobalt creep region, and this would be even higher right here, just like that. So that's pretty much it. So that is exam 2 in a nutshell. We'll see you in the next video. Thanks. Bye.